All right, welcome everybody. This is a short webinar today on fundamentals of Weibull analysis, and this is Fred Schenkelberg. This topic, by far, of all the topics we've offered in the last 2 to 3 years of doing webinars, has been the most signed up for. More people have signed up for this than any of the events that we've hosted. And it looks like we're going to have a pretty good audience, too. It looks like folks are still coming in, but it's going to be busy. We've got a lot of ground to cover. I'm not going to go into the details of regression algorithms and different packages of software. And I noticed in the chat window as we're getting started, I asked people what software package you had. And it looked like Reliasoft, R, and Supersmith. The software packages by Fulton Findings, I think, is where they come from. And if those were mentioned, there may be a few more out there. Weibull++ has been my kind of go-to one for a long, long time. I'm moving slowly over to R because it gives me a lot more versatility, and the types of projects I'm taking on require more of a programmatic type approach. Discrete Weibull, I'm not familiar with that one, Jay, so that one's a new one for me. And I want to preface this by saying today's discussion is not tied to any one software package, and actually I'm not going to show any software output, as a matter of fact. If that's of interest, let me know, and we'll go from there, and may dive into some tutorials and best practices and things like that for different packages. Most of them are pretty straightforward and easy to use. What I found is, though, that people can use software day in and day out and not really know what the analysis is telling them. And that's why I wanted to shift the focus a little bit back to the fundamentals. Looks like we got a couple more votes for Jump and Relics. Relics is old now. I think they got bought. I'm not sure if they changed their name or not, but it's still around, one form or another. But the idea is that we usually start with a pile of data, or we start with a question that we need a pile of data to answer. Does this thing last long enough? Is this thing good enough? Is it, which option is better? All kinds of different things that a pile of data can help us get an idea of, or actually answer a question. And data analysis, whether it's Weibull analysis or log normal regression or creating a Pareto, is generally not a good practice if you're not trying to do one of two things, in my opinion. One is to answer a question. Somebody in the program you're working on says, is this equipment going to last for 5 years with an acceptably low failure rate? Well, if you've got data that talks about the time to failure distribution of that, well, you can answer that question and have a pretty good estimate for it, right? The other part of this is that, do you have data that you need to make sense of, that you're trying to uncover information from, that you're exploring? And maybe you're looking at field failure data and warranty returns information, for example. And now you're looking for, what should we do to make our product better or our system better? And a lot of times that gives you clues or information when the analysis is done well, that lets you ask better questions. Why is that happening? Why is that only happening in Miami and not in Denver, Colorado? Part of the process is to answer questions, and the second half is, when you do a good analysis, is you generally end up with better questions. More questions, but better questions, more focused and more actionable when you get to the answers of it. So let's dive into a little bit about what the general topic is. Weibull analysis, I've heard so many times, and whenever I ask, well, what do you mean by that? Are you just going to pull out a Weibull graph paper and plot it, or just use Weibull++ and do a Weibull curve fit on a Weibull distribution, which is just one of many, many different kinds of distributions that are available to fit data. And in general, people are saying, no, I've got time to failure data, I've got life data, and I need to understand that information. And Weibull analysis has become kind of like Kleenex for a tissue. It's generic for, I'm going to go do some life data analysis or some regression analysis. So I'm using more of a life data analysis approach to this. Yet I named it Weibull analysis because I found that so many people are using that as a generic term for just doing data analysis, for life data analysis in particular. And so I'm not sure if everybody uses it that way or not, but I wanted to make that clear. All right, so before we get into the analysis part, let's talk about life data itself. It's not the same as measuring the dimension of a part. So we wanted to measure a drive shaft, for example, and it's a piece of metal in a cylindrical shape. And we might measure diameter, we might measure surface thickness, we might measure surface roughness, we might measure its weight. Many of those kinds of measurements and the things that are on the drawings for that part, we could measure. Now that tends to be the purview of the quality world and the normal distribution and its related activities. Things like statistical process control and process capability are in that realm and those kinds of measurements. And I think any of you that have, and I see lots of familiar names here today, those that have heard me speaking before know that I think quality includes reliability, and many of the quality people will say that reliability is one of many factors or elements of quality, whereas I say reliability is quality over time. And so life data has this time element. And I'm going to use time pretty generically, right? It could be cycles, it could be missions, it could be sorties, depending on your industry and how your product behaves, it can take on many different elements, but generally I'm going to use time as a go-to for all of these things. And so here we've got time zero. Something is made, it's put into service, it's turned on for the first time, it's installed and commissioned and handed off, whatever it is, right? We sell a product, and over time, the product runs along and it's doing just fine, and then it fails. So I'm going to use the X for it fails. And we shipped a couple of units there, and if I get that one to go, and that one fails, and so on. Right? So it starts at time zero, and then they fail. So at this point, I have 3 units out, and all of them failed at different points in time. And they start at time zero. Now, they could have been shipped. Say this one was shipped in January. For whatever reason, my little cursor here does not like doing curves or writing very much. I should probably use the type tool on this. But anyway, let me back that up a little bit. So the first month, I'll just put numbers here. First month, it's been out there for 3 months and then it fails. And they ship another product in the second month, and it goes out for 2 months and fails, and then so on, right? And the clock starts when it gets put into service or when it's manufactured or when it's available to fail. Let me phrase it that way. And it can vary depending on industry and what information we have and where it comes from and how we use it. Yet what we're interested in is this duration of exposure to the chance that it could fail, right? What's that length of time? And that's what I mean by time to failure data. It could be cycles to failure or sorties to failure or activations to failure or power cycles to failure, whatever it is. Hours of operation is typically what we use in vast majority of products, but it certainly can vary. And so that's what I mean by time to failure data. It's not how many units did I ship today and how long have we been shipping. That's not what I'm interested in. What I'm interested in is how long has the unit been exposed to be available to fail. And so there's some complications to this, of course, is we don't often know. Let me get out of my drawing tab here, and I can hit my cursor. That'll work. We have this concept called censored data. And that just means that we don't have all the information that we really would like. We don't know exactly when it started, and we don't know exactly when it failed. And there's a couple of different ways that can happen. And so censored data, for the folks that on the survey we had at the start that have been here for 15 or more years, and many others of you probably have seen this, but just as a catch-up. Get my pen, let me go. All right, so let's say this something goes out here and it hasn't failed yet. I'm going to use an arrow for that, but this is the day that I'm tallying up what's failed and what hasn't failed. And let's say there was another unit that went out here and it did fail. Now, if I only analyze the failures, I'm using just a subset of only failed units in the system. Yet this unit, this one here, has information that it ran for, say, a couple of months and has not yet failed. So I'm going to use that information to account for, I have a unit that's run for 2 months and it hasn't failed yet, and I have another unit that's run for 2 months and it has failed. And the software packages and even doing it manually, there are techniques for handling the censored data, especially what this is called is write censored data. And I'll just see if I can get an R here, my write censored data. It just means we don't know what's going to happen to the right of this on the timeline. It could fail at that moment after we looked at it and said, yeah, it's still working, or it could fail many years from now. We just don't know. But what we do know is that it's run from its start time to now. Now, another case is we don't know when it started. We don't really have we know that at some point it was running, but we don't know when it started. We don't know when it was installed or put into operation. And it could either be still running or it could be failed. But in this case, we call it left censored. So we don't know the opening of. This isn't as common, and you need to really pay attention to how you analyze this data, but it's very similar in nature to the right censored in that we have this uncertain area. In right censored, it's over here. In left censored, it's on the left side. Hence their two names. A third kind, of course, is when we don't know either left or right. We just know that it's run for some period of time in between some inspection points of some sort. Yet there's another kind that we only check it on occasion. So let's say it's run for some period of time, and we've just checked it at this point, and it's still running. And we checked it at this interval, say a monthly PM, for example. So we know it was running here, and we know it was running at the start. Okay? So in this case right now, I'm right censored. Let's say it's running out to our next time we go out and check it or turn it on or whatever, and it's failed. But we didn't notice the failure when it actually occurred. We only noticed the failure the next time we went out to inspect it. We didn't have an ongoing diagnostic, so we don't know whether it failed moments after we left it before, or did it fail moments before we inspected it the second time. So this is called interval censoring, and there are 3 different ways you can handle that. One of them is you be very conservative and says it failed early, right? You can use it failed right after the last inspection, or you can be very optimistic and say, well, it failed moments before I checked it. And you get all of this duration and time that makes it work. And the other way, and this is the most common one that I've seen, is you put it in the middle of the interval. And so the way you treat the interval censoring takes a decision and how you're going to handle it. And it changes the results of your analysis slightly, but it shouldn't make an overall big difference if you're consistent with how you go about doing it. So that's one thing to keep in mind is there's right censored, left censored, and interval censored, and it affects how you interpret the data and include it all. Now, one thing to be very cautious of is if you have, say, 50 units that are running and they're still running, they're going to be right censored. Don't ignore those if you have 50 units that have failed already and just analyze the failed data because you're leaving a lot of information on the table and it's not available for you. You should use that information, those durations that they've run up until they become right censored and include that in the analysis. So 3 different ways the data can be presented to you. Time to failure and are also censored. All right, so I've gone long enough without asking. Yeah, and Mark, you're right. Oftentimes they're called suspensions. Is another way they're called in some different software packages, and I think it's where they went to school or what book they used is suspensions or censored. But where do we find life data? Where's this stuff come from? So if you could jump back up on the chat window and where's my pen? Where do we find life data? What are some ideas there? Yeah, warranty returns, easily. Yeah, it's the easiest one. One of the hard parts with warranty data is that, especially consumer products, is we don't know how many units have been put into service, have worked admirably for, say, a year or 2 years or longer, and are still in use. They may have been retired or put on the shelf or upgraded because usually there's not unless your product actually talks back to the mothership, it doesn't really give us a bunch of information about how many are still there. And some people assume everything's still operating. Others do surveys and find out from their customers how many are still in operation. That makes it a bit murky. You just need to make clear assumptions there, make it clear. Accelerated testing, durability testing, field data, teardown reports. Jay, on that, yeah, you can get some life data from that, especially when things fail but don't cause the customer to notice it. For example, you may have a wear pattern or so on that can project out to a failure. Corrosion reports, yep, Vandar, exactly, the CMMS. It's in so many organizations, that at least the ones I've been into that are factory and asset management type organizations, is they have the CMMS, they're recording all of these different repairs. The ones that do a better job at failure analysis and actually get and record it is invaluable data. It really, really is useful. Yeah. And returns can be underreported, especially for lower price products. It's not worth my time to get on the phone and report a problem or a failure. Or if I know that it's only a 6-month warranty is offered on it, or I know I'm well past the warranty period, I'll just save the time and go back to replace the product or move on to something else. And so that information does get lost. Other products, I'm thinking of like a Fitbit that talks to a server regularly. There you've got access to data that when it's been charged, when it's been used, how it's, some information about how it's used and so on. And then when it goes dormant or quiet, they may be on a vacation and forgot it, or they actually shelved it, or it's failed. And so there's still lots of uncertainty in our data. What I find is whether we do it working with our vendors to get their test data or information or their field data, working internally with our own programs to evaluate products and to do accelerated testing or durability testing, or looking at our field data in its variety of different ways we can get access to it. I had one group that they wanted to find out information about fans, these little cooling fans for these servers. They had horrible data from the field and the repair centers that were repairing them. But what they did is they looked at the stock room and how many of these fans with the unique connector it had were being ordered per month, and then worked backwards to figure out some information there. By no means was it perfect, yet it gave them some clues as to what's the failure rates they were seeing. Yeah, and you're right, Mark. If it's we get some stuff through our supply chains, we get some stuff anecdotally. More and more companies are now on social media and sites like Yelp, a review site, or Amazon and the review site, looking for those anecdotal evidence of failures and natures of failures, is to supplement their internal stuff. It's not as expensive of running a survey. Yeah. Yeah, and Daniel, good question. I'm just reading your question here. So you have a brand new product. You don't have any in the field yet. You don't have a whole bunch of information there. And, the typical pattern is, yeah, what if I take 100 of our prototypes and run them for 2 years and a long life test and really understand and answer that question? Well, that generally isn't an option for most products that we're working on. And so it becomes a mixture of engineering judgment. Oh, this is solid. We've used something similar to this in another design and another product. Or this is uncertain. We don't know. So let's run an internal accelerated test and understand that part. Some we can do at system level. Some we have to do at component level. Some data will come from our vendors. And some vendor data is just not worth using. So it's what I recommend in those cases, the one you just outlined, Daniela, is to do a reliability block diagram and use your best estimates for each block. So the example I use all the time is if I had say a computer system. Oops, here's my system. I have no idea why I can't draw curves easily with this cursor. Anyway, here's my system. And let's say I have 5 blocks. Motherboard, and we call out the CPU because it's a big subsystem, the monitor and keyboard, and we have a hard drive, and so on. So let's say we have 5 major elements. Power supply, always my favorite. I'll use this strange one for the power supply. So what we need is an estimate for each of these things. Now let's say the CPU is brand new, yet it's a new technology, say a smaller dimension size to it. So we may want to do some accelerated life tests or work with the vendors to get some estimates and so on. And the keyboard guys, though, are saying, our field data, the keyboard really hasn't changed, the same technology. It should be solid. Here's our reliability estimate, say 99.9% over 2 years. And no need for testing. We've got anecdotal evidence and engineering judgment backs it up. The power supply, though, we're looking at different vendors. And we go to them and look at their data and how they analyze and estimate the reliability. If they're doing a parts count prediction, I'm going, that's not terribly useful. Let's run some accelerated tests. Let's understand what's going to fail and when, and create our own distribution there. And then for the 2-year point, we can pull off the reliability and populate the block diagram. And then it's a matter of, in this case, a series system. So then we multiply out the reliabilities to get our system reliability estimate. And so in some cases, we just don't have great data for every piece of our system. And there the focus is on, well, what are the risky elements? What are the most uncertain elements? What are the areas that have the least margin? And so those areas then require the investment to find out better answers. And it could be physics of failure modeling, it could be component level testing or component or coupon testing, or it may be a full blown accelerated life test that's creating a new model to understand that product's response to a particular set of stresses. So the answer, Daniela, could actually be a multi-day course, but in general, we have lots and lots of data around us, the warranty data, the in-house testing data, um, even those guys over in the software team that are running firmware checks and modeling their software on systems. Those systems have to run. So if they fail, we should track that. It's actual operating time and types of failures that occur really shouldn't be happening, but they also contain a lot of information. So tracking those is also useful. A little bit of creativity, I'm sure everybody here can find lots of data. So let's take a look at